can do the recording, right? So, I'm going to get you inducted into parts of modern physics. My agenda for the class today is going to be photoelectric effect, so this entire business of photoelectric effect was initially observed when this gentleman Heinrich Hertz was performing an experiment in his lab, and he was producing electromagnetic waves. He was producing electromagnetic waves using an LC circuit. That was the experiment that he was carrying out. And in his experimental setup where he was producing electromagnetic waves, there was a spark that was being generated. There were two metal spheres, M1 and M2. And he suddenly found that when the electromagnetic wave, he was actually generating ultraviolet rays, UV rays, ultraviolet. And he found that when one of the metals was struck with the ultraviolet rays, the spark between the two metallic spheres increased. Spark increased. Now, spark can increase only if there is flow of charge from one metal sphere to another. If there is additional flow of charge, that's where there would be an increased spark. So that's when he said, all right, what really might be happening is when this ultraviolet rays struck one of the metal spheres, then what must have been ejected out of this metal sphere, what must have been liberated out of this metal sphere must have been electrons. More electrons must have been liberated from one of the metallic spheres, adding to enhanced spark. This was really the foundation that led to further investigation of the effect, which I'm going to discuss at length today, which is the photoelectric effect, which is essentially about the following. If there is a metallic surface, if this is a metal, and if there is a radiation of a certain frequency, electromagnetic radiation of a certain frequency, F, then what happens is, under certain conditions, one might observe liberation of electrons from the surface. There could be liberation of electrons from the surface. This effect was essentially photoelectric effect. This is essentially was photoelectric effect. However, there is more to it than just this. So, the theory of photoelectric effect is based on the following foundation and on the following premise. Electromagnetic waves they are in a certain sense quantized in terms of energy. They have energy, electromagnetic waves. They are quantized in terms of the energy that they carry. if nu was the frequency of the wave, nu was the wave frequency, then what was postulated? What was postulated? That this electromagnetic wave contained packets of energy, packets or bundles of energy, referred to as photons. The electromagnetic waves carried bundles of energy or packets of energy. Energy was propagated by means of packets or bundles of energy or quanta of energy in the form of bundles or particles called photons. That means if this was an electromagnetic wave, I can conceive this to comprise of several bundles of energy called photons, and if nu was the frequency of the wave, then each photon carried a certain quantum of energy. E, which was h nu. H was a constant. H is a constant called the Planck's constant. Planck's constant, and its value its value in SI is 6.63 into 10 to the power minus 34 joules second. Realize that this is joule second, this is per second, so this will be energy in joules. This would be energy in joules. So every bundle of energy carried by an electromagnetic wave is a photon, and the amount of energy in each bundle is going to be E equal to h nu. H is Planck's constant, whose value is 6.63 into 10 to the power minus 34 joule seconds. Nu is the frequency of the wave that is carrying these bundles. Now, these photons had certain basic properties. So one thing for sure, the total energy carried by the electromagnetic wave would always be an integral multiple of h nu, because there would be an integral number of photons. That's why we say that the energy is quantized. It will exist only in integral multiples of a certain quantity h mu, which is the energy carried by a photon. Now, very clearly, if it's a high frequency wave, that is, if nu is high, then the energy carried by the wave is higher, because each photon carries more energy, h nu. Each photon will carry more energy, h nu. E, energy carried by photon, will be high. So high frequency waves are also high energy wave in a certain sense, because every quantum is higher. Every quantum is h nu and is higher than a lower frequency wave. Also, these bundles of energy, the photons, the bundles of energy, the photons, essentially have no rest mass. and they have no charge. They have no charge. They have no rest mass and they have no charge. They move with the electromagnetic wave, forging the energy forward with a velocity equal to velocity of light. Velocity of light, which is 3 into 10 to the power 8 meters per second. Pressure and temperature conditions don't affect them. Pressure and temperature conditions don't affect them. Now, these are some very basic properties of a photon. Also, realize that this energy E of each photon carried by a wave that has frequency nu can also be written as frequency is wave velocity, which is c, divided by the wavelength of the wave. Lambda is wavelength of the wave. This is the energy of a photon. This is the energy of a photon. Now we have what is called a energy mass equivalence. Courtesy Einstein. If m is the mass equivalent of a photon, there is nothing like an actual mass of a photon, but there is a mass equivalent of a photon. There is a mass equivalent of a photon. Can I wipe this off if you have finished copying this?
Yes, sir.
Yes, sir.
Yes, sir.
E is the energy of a photon. And if m is the mass equivalent of a photon, then E is mc squared. C is the velocity of light. Then this amount of energy is equivalent to this amount of mass. This amount of energy is equivalent to this amount of mass, where m is the mass equivalent of a photon. M is the mass equivalent of a photon. C is the velocity of the photon, the velocity of the wave. Now, so hc by lambda or h nu is the energy carried by a photon, which is mc squared, where m is the mass equivalent of the photon, and mass into c is the momentum, equivalent momentum of the photon. Photon. So this I can write as mc into c. So hc by lambda, the energy, can be written as mc into c, mc square.
Yes, sir.
And this is the linear momentum of the photon, p. P into c is hc by lambda, linear momentum of the photon, equivalent momentum of the photon. P then is h by lambda. Linear momentum P of a photon is h by lambda. So this is like an equivalent momentum. You know, in a quantum domain or quantum mechanics domain, it's a different concept. Unfortunately, we can't dig very deep into it, but for the time being, this is not really the momentum, but an equivalent momentum concept of a photon. This is the energy of the photon. And this is like an equivalent mass for a photon. When that entire energy translates into a mass m, it's mc square. And this is how we look at energy and momentum of a photon. The momentum is h by lambda, energy is hc by lambda. Now, can I write this off?
Yes, sir.
Yes, sir.
Realize that the energy of a photon, energy carried by a photon, is hc by lambda, energy carried by a photon, where h, realize, like I said, is 6.63 into 10 to the power minus 34 joules second. C, velocity of light, is 3 into 10 to the power 8 meters per second. And lambda is the wavelength of the wave. Lambda is the wavelength of the wave. जितना कम wavelength होगा, उतना energy ज़्यादा होगा of the photon of the wave. Low wavelength means high frequency, high energy, right? Now, in the atomic domain, quantum mechanics domain, energy is best measured not in joules, but in electron volt. Well, what's an electron volt in terms of joule? 1 electron volt is like charge on 1 electron, 1.6 into 10 to the power minus 19 coulombs. Coulombs into volt is joules. QV is joules, right? So this is like 1.6 into 10 to the power minus 19 joules. 1 electron volt. Electron volt is the unit of energy that we will predominantly look at in modern physics. Electron volt. 1 electron volt is 1.6 into 10 to the power minus 19 joules. And therefore, very clearly, 1 joule would be 1 electron volt by 1.6 into 10 to the power minus 19 electron volts. Each joule is like 1 by 1.6 into 10 to the power. Each joule is like 1 by 1.6 into 10 to the power minus 19 electron volts. Right? So, H into C, realize H into C is clearly H, which is 6.63 into 10 to the power minus 34. C is like 3 into 10 to the power 8. This is like these many joule meters, isn't it? This is like these many joule meters.
Yes, sir.
Right? But this lambda is not measured in meters. This lambda is normally measured in nanometers or angstroms wavelength. Right? So what we should do is we should try and convert this joule into electron volts and this meter into, say, angstroms or nanometer, right?
Yes.
So what I do is 6.63 into 10 to the power minus 34, 3 into 10 to the power 8. Each joule, as you can see, is 1 by 1.6 into 10 to the power minus 19 electron volts. So joule to electron volt mein convert ho gaya by dividing by 1.6 into 10 to the power minus 19. Joule has got converted into electron volt. Meter को convert करना होगा तो कैसे करोगे? 1 meter is 10 to the power 10 angstroms. 1 meter is 10 to the power 10 angstroms. Yes or no?
Yes, sir.
Yes, sir.
So then the unit of HC now can be written in terms of electron volt angstroms.
Yes, sir.
ये roughly कितना आता है? अब ये देखो 10 to the power 19 यहाँ चला गया, 10 to the power 19, 10 to the power 27, 10 to the power 37, 10 to the power 3, 3, 5, 1.23. roughly देखो यहाँ order of magnitude दिख जाएगा 10 to the power 18, 10 to the power 19, 10 to the power 37 into 10 to the power minus 34, 10 to the power 3, ये करीब 10 to the power 3 यहाँ से आ गया, and then I have 3 cancelling this, yeah 3 cancelling this roughly 5 times, roughly 1.2 times, so roughly 1.2 into 10 to the power 3, roughly 1200. इसका exact value हम बता देते हैं without, you can use the calculator to check this out. This will roughly turn out to be 12,400 electron volt angstroms. It will roughly turn out to be 12,400 electron volt angstroms. Yeah, 1 angstrom is 0.1 nanometer. 1 angstrom is 0.1 nanometer. तो ये 1 angstrom की जगह 0.1 डाल दोगे तो ये 1240. So this is the same as 1240 electron volt nanometer. Electron volt nanometer. So HC could be looked upon as 12,400 electron volt angstroms, or could be looked upon as roughly 1240 electron volt nanometer.
Yes,
These are
sir.
two important numbers you must remember. Hc of this energy of a photon is like 12,400 electron volt angstroms, or 1240 electron volt nanometer.
Yes, sir.
So energy of a photon, if you want to compute in electron volts, if the energy of a photon has to be computed in electron volts, then write this as 12,400 electron volt angstroms divided by lambda in angstroms. So angstrom will get cancelled. So you get 12,400 by lambda in angstroms will give you that many electron volts. Yes or no?
Yes, sir.
Yes, sir.
Or roughly 1240 electron volt nanometer divided by lambda in nanometer. So if you use lambda in nanometer, then the numerator should be 1240 electron volt nanometer. Nanometer will get cancelled. You'll get energy in electron volt of a photon.
Yes, sir.
Right, so should remember this. It'll save calculations because most of the time energy will be computed in electron volts. ठीक है, lambda अगर angstrom में use करना है तो use HCS 12,400 electron volt angstroms. Lambda, if you want to use a nanometer, then 1240 electron volt nanometer should be our HC, so that this eventually becomes electron volts, right?
Yes, sir. Yes, sir.
जैसे typically, how do you compute the number of photons in a certain amount of light or electromagnetic wave? How does one compute number of photons? So suppose I have a 100-watt sodium vapor lamp. Suppose I have a 100-watt sodium vapor lamp. The wavelength of a sodium vapor lamp, sodium vapor is light of wavelength 5893 angstroms. इसका सोडियम लाइट का वेवलेंथ होता है 5893 एंगस्ट्रॉम्स होता है. और एक 100 watt lamp is emitting sodium light, sodium vapors, that is wavelength 5893 angstroms. तो what does this do? This is doing like 100 joules per second of energy it is emitting.
Yes, sir.
100 joules of energy per second it's emitting, divided by energy per photon, energy in joules per photon, will give me the number of photons per second it is emitting.
Yes, sir.
Yes, sir.
See, it's emitting 100 joules per second. उस 100 joules में कितना photons है? Divide by the energy per photon. Energy
Yes,
in joules per photon will give me number of photons per second.
Yes, sir.
yes, sir.
Yes, sir.
Will give me number of photons per second, which is like 100 divided by energy of a photon is hc by lambda. Energy of a photon, right?
Yes.
अब ये तो जूल्स में, तो इसको भी जूल्स में ही लिखना होगा सारा, इसमें इलेक्ट्रॉन वोल्ट नहीं चलेगा, right? So which is like 100 divided by h. H is 6.63 into 10 to the power minus 34 into c, which is 3 into 10 to the power 8 divided by lambda, 5893 angstroms into 10 to the power minus 10 meters, right? These many photons are emitted by this bulb every second. This is the number of photons emitted per second, right? Total energy per second divided by the energy per photon will give me number of photons per second, isn't it?
Yes, sir.
Per second. अब कोई बोले कि ये लैंप है, ये in 2 hours how many photons will be emitted? In 2 hours means 2 into every hour is like 60 minutes into 60. These many seconds?
Yes, sir.
7,200 seconds में कितना photon emit होगा? Multiply this with 7,200. You will get the number of photons emitted by this 100-watt sodium vapor lamp emitting light of wavelength 5893 angstroms in 7,200 seconds. It will emit into 7, multiply by 7,200, we will give you the number of photons emitted in that much of time.
Yes, sir.
Yes, sir.
Acha, ab ye, you know, this is photons per second, right? This is photons per second. Now this is, say, the 100-watt lamp, and say it's the entire energy falls on a surface. Say this was my 100-watt lamp, and the entire energy from this 100-watt lamp, say theoretically as a cylindrical le this entire energy of this 100-watt lamp falls on a surface of area A, passes through a surface perpendicular to an area A. This 100 watts of energy is passing through an area A perpendicular to the area A. Then we say intensity. Intensity is like watts per meter squared per unit area. So that's going to be 100 divided by E. Is the watts per meter square. Is the watts per meter square. That's the intensity. Intensity is hamesha how much of energy is passing a unit area perpendicular to the direction of wave propagation. Perpendicular to the direction of wave propagation, how much of energy is passing per unit area, that will give me intensity of the wave. अब जैसे कि कोई बोलेगा, can I wipe this off?
Yes,
Yes,
sir.
sir.
Suppose somebody said there is a area A. ठीक है, perpendicular to this area, there is a radiation of intensity I. Perpendicular to this area, there is a radiation of intensity I. Intensity मतलब क्या हुआ? Watts per meter square. Right?
Yes, sir.
Now, if somebody says, how many photons are striking this area per second? Each second. Each second. Intensity is obviously about an area perpendicular to the direction of propagation. Okay? So this is the area A that I'm talking. इसमें कितना photons पड़ रहा है? That's a question we want to answer. Okay? अब I is the intensity. Intensity watts per meter squared मतलब joules per meter squared per second. This amount of energy, I joules of energy, is falling per second per meter squared. अब I joules में कितना photon होगा? Divide by the energy per photon will give me the number of photons. I joules है ना? I joules, I intensity, I joules per meter square per second. तो I joules में कितना photon होगा? hc by lambda, क्योंकि every photon has an energy hc by lambda joules.
Yes, sir.
Right? This is joules per photon. So what will this give me? This will give me I by hc by lambda photons falling per second per meter squared. Photons falling per second per meter squared on this area. हर यूनिट एरिया में इतना photons गिर रहा है. I by hc by lambda, right?
Yes, sir.
Yes, sir.
तो over an area A, ये तो 1 meter square का area है. So if there is an area A, number of photons falling on the area A per second is I by hc by lambda. तो ये तो number of photons per unit area per second. So multiply by A will give me photons per second. Photons per second falling on this area.
Yes, sir.
Right?
Yes, sir.
Yes,
sir. Yes, sir.
Can I write it out?
Yes, sir.
Yes, sir.
अब कोई ना suppose there is an area A like this, ऐसा, ठीक है? There is a beam of light that falls. There is an incident radiation that falls on this area A. ये area A ऐसा, ठीक है? जिसपे there is I is the intensity of radiation falling. पर सीधा नहीं गिर रहा है, normally नहीं गिर रहा है. It is falling at an angle theta with the vertical. At an angle theta with the vertical. Then the question, suppose I is the intensity of the ray. In this case, how many photons strike this area A? How many photons strike this area A per second?
I cos theta लेना पड़ेगा.
अब क्या करो ना? I is about an area perpendicular. I is about an area perpendicular to the direction of propagation. ये direction of propagation है, ये area A है, उसका projection perpendicular to the direction of propagation. ये area A है, ये angle theta है, ये theta है, तो ये 90 minus theta होगा, ये 90 degrees है, ये theta होगा. Very clearly, this area A would be A cos theta. This area A would be A cos theta. Right?
Yes, sir.
Yes, sir.
I watts per meter squared is about this area A. That means total energy falling, total number of photons falling on this area would be the number of photons incident on area A. Right? अब यहाँ पे कितना photons गिर रहा है? कितना photons गिर रहा है? Total energy falling कितना है? Total energy falling would be I into A cos theta.
Yes, sir.
These many joules per second is falling. I
Yes,
is watts per meter squared per second, है ना? उसको अगर एरिया से मल्टीप्लाई करोगे a cos theta से, तो you will get what? So this is joules per meter. जो watts is joules per second per meter square. If I multiply this with area कौन सा area से multiply कर सकते हो intensity को? Area which is perpendicular to the direction of wave propagation. ठीक है? So a cos theta. So this will give me joules per meter square per second into meter square will give me joules per second. Is the
Yes,
energy
sir.
incident?
Yes, sir.
अब
Yes, sir.
these many joules per second I a cos theta में कितना photons गिर रहे हैं? I a cos theta joules में कितना photons होगा? Photon का energy hc by lambda होगा. These many photons per second. These many photons per second are falling on this area. Right?
Yes, sir.
Yes, sir.
These many photons are falling on this area. Yes or no?
Yes, sir.
Because intensity को कौन से एरिया से मल्टीप्लाई कर सकती हो टू गेट joules per second? Intensity is joules per meter square per second. To get joules per second, what area would you multiply it with? Area which is perpendicular to the direction of it. Right?
Yes, sir.
Now, let's get down to some computational stuff, some equations, some algebra, and so on and so forth. So what happens is, ये एक metal surface है. On this metal surface, on the surface, there are free electrons. On this metal surface, there are free electrons that are moving because of their thermal motion. Thermal motion, right? Now, because of their thermal motion, what could happen is electrons, free electrons, in thermal motion. They're randomly moving surface पर. Now, it is possible that this electron escapes this surface. पर जैसे ही वो escape करने का कोशिश करेगा वो electron, what will happen is if an electron tries to escape, then this surface will become positively charged because it has one electron less.
Yes, sir.
ये negatively charged है, ये positively charged है. So what would happen is the positive charge will pull the electron back. Electron में दम होना पड़ेगा, बहुत kinetic energy होना होगा so that it can overcome this attraction with the surface and leave the surface forever. You know what I'm saying?
Yes,
Yes,
sir.
Yes, sir.
The electron should have enough kinetic energy so that it can leave the surface. Yeah, you have to supply some energy to the electron so that it can leave the surface. Otherwise,
Yes, sir.
the moment it just comes out, barely comes out of the surface, the positive charge here pulls it back and it goes back into the surface. So the energy of the electron has to be high enough for it to be capable of leaving the surface. Yes or no?
Yes,
Yes,
sir.
sir.
So one way. So you have to somehow energize the electron for the electron to leave the surface. Right? You have to somehow energize the electron. देखो essentially क्या होता है ना? Essentially what really happens is essentially what happens is, these electrons, after all, they have free electrons, so they would have left positive ions here in this region. They would be positive ions, right? Because some planetary electrons would have left the atom and are moving freely in a metal, right? Planetary electron tha, wo leave kar gaya outer shell se, free electron ban gaya, which happens rampantly in a metal.
Yes,
Right?
sir.
And so there are positive ions in the metal. So, there are attractive forces that hold the positive ions and electrons, preventing the electrons from leaving the surface.
Yes, sir.
Yes,
Right?
sir.
Yes, sir.
But if you, there is essentially every electron has a certain amount of potential energy because of its attractive force with the surrounding positive ions. Every electron has a certain amount of potential energy, and we call it a potential barrier. वो साला ये potential energy छोड़ के निकल नहीं पा रहा. It is not able to escape, get liberated by leaving this potential energy, right? But if you bombard this electron with some amount of energy, it then acquires the stamina. To leave the surface. It may leave the surface. If you energize the electron, it may leave the surface. It may overcome the barrier, which we call the potential barrier. The electron may overcome the potential barrier and may leave the electric field of the positive ions. It may leave the electric field of the surrounding ions. Right?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So actually, fundamentally, from an electrostatic point of view, suppose the potential energy is 5 electron volt for an electron here because of its surrounding. Okay, right? Or वो negative होगा. In a certain sense, that will be negative, right? So realize that positive and negative charge के बीच में the potential energy is negative, isn't it? K Q1 Q2 by R, if one is positive, one is negative, then the potential energy is negative, right?
Yes, sir.
Right? अब ये -5 electron volt है इसका energy, electron का. If you want it to escape to infinity, मतलब इसका energy 0 बनाना पड़ेगा.
Yes, sir.
इसका
Yes,
0
sir.
कैसे बनाओगे? इसका 0 अगर इसको 5 इलेक्ट्रॉन वोल्ट दोगे ना, तो इसका एनर्जी 0 हो जाएगा, ये इंफिनिटी में जा सकता है. मींस इट कैन ओवरकम द बैरियर एंड गो टू इंफिनिटी.
Yes, sir.
That means how much of energy you would have to supply. So if this 5 electron volt is its potential barrier, इसका ये जो -5 electron volt potential energy है ना, वही इसको prevent कर रहा है from leaving the surface, which is minus is indicative of the fact that it is remaining glued to the surrounding ions. Surrounding ions are preventing it because of this momaya. -5 electron volt का potential energy is its momaya. It's preventing the electron from leaving the surface. अब इसका मोमाया से दूर करने का क्या तरीका है? You will have इसका potential energy 0 बना दोगे तो it's as if it can go to infinity where it has 0 potential energy.
Yes, sir.
Infinity में जाने के लिए तो इसको 0 potential energy दे का वो देना होगा ना लालच.
हाँ, sir.
Yes, sir.
Because at infinity its potential energy will be 0. तो इसको 5 इलेक्ट्रॉन वोल्ट दो. तब बोलते हैं ठीक है भाई, अब मैं लीव कर सकता हूँ सर्फेस. I can leave the surface and I can escape the. So ये इसका potential barrier. This is its potential barrier, which is a property of the metal, So the electron has a potential barrier The electron has a potential barrier which it has to overcome to be able to leave the surface of the metal. Right? Yes or no? Hello? But if you can supply this amount of energy, its energy can become zero and it can escape the metal surface. It can escape the metal surface, right?
Yes, sir.
Yes, sir.
But that means there is a smallest amount of energy that every electron must be provided so that it can leave the surface, which let's say is 5 electron volt. Say 5 electron volt for some metal. Okay. ये metal का property है. ये potential barrier जो है ना, यहाँ पे 5 electron volt है potential barrier इसको 5 electron volt energy दो तो ये leave कर देगा because उसका net energy 0 हो जाएगा उसके बाद. It can leave the metal surface and escape to infinity, right? But ideally, yes. इसको तुम 5 electron volt दोगे. Energy in some form or the other. कैसे कैसे दे सकते हो? You can give it 5 electron volt energy, for example, by heating this, which is thermal agitation, right? One way to provide it is thermal agitation. Heat it. Heat. And if an electron gets emitted because of heat देने से उसका वो energize हो जाता है, उसका net energy 0 बन सकता है, and it can leave the surface, right? That emission of electron is called thermionic emission. That's one way. But the point is, no matter what the mode of giving energy to the electrons is, right? I could also energize these electrons by bombarding with other electrons. Bombarding with stream of electrons. Or say high energy electron stream comes and strikes the surface. It collides with these electrons and imparts energy to these electrons. And it can get that minimum amount of energy. So what's the minimum amount of energy? Let's say this electron needs to overcome the surface. For example, in this case, 5 electron volt. To 5 electron volt, usko energy milte hi, it will be on its way out of the surface. It will try to escape the surface. ठीक है? वो heat से दे सकते हो या bombarding with stream of electrons दे सकते हो. There can be other ways of imparting energy to the electron. There can be other ways. There could be multitude of ways of imparting electrons with the amount of energy. Let's say in this case 5 electron volt, which is the minimum amount of energy it requires to escape the surface. Right?
Yes,
Yes,
sir.
sir.
But ये जो minimum amount of energy an electron be given so that it could overcome the potential barrier and escape the free surface, escape the metal surface. Is called
Threshold feedback.
work function W. Is called the work function W of the metal. ये metal का property है. Different metals will have different values of work function. Generally, say for it ranges from around 1.2 electron volt. I think cesium ka hai 1.2 electron volts. I'm not sure of these values. And say around 5.6 electron volt. I think platinum ka you want to check, but generally around 1.2 to 6 electron volt is the work function of metals. It's an experimentally obtained value, the work function of every metal.
Yes, sir.
हर मेटल का ये प्रॉपर्टी है which is documented.
Yes, sir.
So the moment you supply, let's say if this metal has work function 5 electron volt, that means it has potential energy minus 5 electron volt. It should be reduced to 0. So moment you supply it 5 electron volts, it starts to plan its journey out of the surface. The moment you supply an energy to an electron equal to the work function of the metal, it starts to plan its journey out of the surface. Right?
Yes, sir.
Yes, sir.
Now, there are two kinds of electrons. ठीक है, एनर्जी दिया. अच्छा, अब क्या होगा? तुम 5 इलेक्ट्रॉन वोल्ट इसको एनर्जी दोगे तो इसका एनर्जी 0 हो जाएगा. पोटेंशियल एनर्जी ये जस्ट बाहर आ जाएगा, इसका काइनेटिक एनर्जी 0 रहेगा उस इलेक्ट्रॉन का. अगर ये बाहर आ गया तो ये इसका काइनेटिक एनर्जी 0 होगा. पर before I tell you that, don't bother about this right now. What really happens is, the moment I give this electron, say work function 5 electron volt, moment I give this electron an energy equal to 5 electron volts, ये energy दिया electron, अब इसका capability है बाहर निकलने का with 0 kinetic energy. I've supplied it an amount of energy just equal to the work function of the metal, then it has just about got the threshold amount of energy so that it can escape the surface. Just उतना मिला है कि surface के बाहर आ सकता है, उतना है capability उस electron का. पर यहाँ पे जो electrons मंडरा रहे हैं, the electrons that are hovering over close to the surface, यहाँ पे ना दो तरीके के electrons हैं. Electrons on the surface are two kinds. एक है आवारा इलेक्ट्रॉन्स, बहुत आवारा. ये बेटा इसको एनर्जी मिल गया, ठीक है. अब ये बाहर निकलने की जगह है ना, क्या करेगा, और सब इलेक्ट्रॉन्स के साथ कोलाइड कर कुरा के अपना एनर्जी खत्म कर देगा. बाहर ही नहीं रहा, जहां था मेटल में ही नहीं. आवारा इलेक्ट्रॉन है ये, है ना. एक किस्म का इलेक्ट्रॉन क्या है, आवारा इलेक्ट्रॉन है. उसको तुम वर्क फंक्शन जितना दे दियो, उसको एक अपॉर्चुनिटी दियो कि भाई तू बाहर निकल सकता है, पर वो बोलता है रुक, अभी मैं एनर्जी इसको इधर उधर इसके साथ कोलाइड करके मारपिटाई करके खत्म कर दे. पाड़ा का गुंडा है वो.
Yes, sir.
एक तो आवारा इलेक्ट्रॉन है. और एक इलेक्ट्रॉन है समझदार इलेक्ट्रॉन। ये एग्जाम में मत लिख देना, समझदार इलेक्ट्रॉन, वाइज इलेक्ट्रॉन। वो बोलता है कि मेरे को 5 इलेक्ट्रॉन वोल्ट दिया है, नेचर हैज गिवन मी एन अपॉर्चुनिटी टू एस्केप द सरफेस। वो ना बिना कोलाइड किए बाहर निकल आता है, पर वो जब बाहर निकलता है ना बिना कोलाइड किए, तो वो 0 काइनेटिक एनर्जी से निकलता है। उसका -5 था पोटेंशियल एनर्जी, तुमने उसको 5 इलेक्ट्रॉन वोल्ट और दिया, तो उसका नेट एनर्जी 0 हो गया, तो काइनेटिक एनर्जी भी 0 हो गया उसका। तो इट इज दैट समझदार इलेक्ट्रॉन when provided an energy equal to 5 electron volt just escapes the surface without kinetic energy। ठीक है बेटा?
हाँ
हाँ
सर।
सर। यस सर।
आवर इलेक्ट्रॉन को 5 इलेक्ट्रॉन वोल्ट देने से फिर भी खत्म करता है। ठीक है, अब सोचो, सपोज द सेकंड पॉसिबिलिटी इज, से if we supply 9 electron volt energy to the electron, ठीक है? तो सोचो एक आवारा इलेक्ट्रॉन, ये मेटल सरफेस है, इसको तुम इस इलेक्ट्रॉन को 9 इलेक्ट्रॉन वोल्ट सप्लाई किए, ठीक है?
यस सर।
अब ये क्या करेगा ना, ये देखेगा कि थोड़ा सा एनर्जी हम कोलिजन वोलिजन में खत्म कर देते हैं। 9 इलेक्ट्रॉन वोल्ट का मैं सम एनर्जी से 3 इलेक्ट्रॉन वोल्ट कंज्यूम्ड इन कोलिजन्स। अपना दोस्त यार से मिल रहा है बेटा, मारपीट करके 3 इलेक्ट्रॉन वोल्ट खत्म कर दिया। बचा इस ससुरे के पास कितना एनर्जी? 6 इलेक्ट्रॉन वोल्ट। अब 6 इलेक्ट्रॉन वोल्ट में क्या हुआ? 5 इलेक्ट्रॉन वोल्ट कंज्यूम हुआ टू एस्केप द सरफेस, सरफेस के जस्ट बाहर निकला। समझ रहे हो? 9 में से 3 बाजार में चाट पकौड़ी खा के खत्म कर दिया, दोस्त यार को खिला पिला दिया, और दोस्त इलेक्ट्रॉन था उनके साथ भीड़ भिड़ गया। 5 इलेक्ट्रॉन वोल्ट यूज किया टू एस्केप द सरफेस, जो इसको चाहिए सरफेस को, टू ओवरकम द force of attraction with the surrounding positive ions, to just about escape the surface it needs 5 electron volt। बाकी इसके पास अभी भी एनर्जी बचा 1 इलेक्ट्रॉन वोल्ट। अब ये एनर्जी कहां जाएगा? ये जो बचा एनर्जी है ना, उसके काइनेटिक एनर्जी में रहता है।
यस सर।
काइनेटिक एनर्जी। सो एक रियल इलेक्ट्रॉन आवारा इलेक्ट्रॉन होता है। एक रियल इलेक्ट्रॉन जो है ना, वो आवारा इलेक्ट्रॉन हो, उसको कुछ एनर्जी दोगे ना, तो वो कुछ कंज्यूम होगा कोलिजन्स में, कुछ कंज्यूम होगा टू एस्केप, और बाकी अगर बचा रहा ना तो वो काइनेटिक एनर्जी। पर कुछ इलेक्ट्रॉन्स ऊपर ऐसे भी है, ऐसा नहीं है कि सब इलेक्ट्रॉन सिमिलरली बिहेव करेंगे। कुछ इलेक्ट्रॉन्स हैं जिनको 9 इलेक्ट्रॉन वोल्ट दिया तुमने एनर्जी, वो सारा का सारा दोस्त यार में खत्म कर दिया।
यस सर।
कुछ इलेक्ट्रॉन है जिसको 9 इलेक्ट्रॉन वोल्ट दिया, उसमें सोचो 9 का 9 खत्म कर दिया दोस्त यार के साथ, तो उसके पास कुछ बचा नहीं, वो भी नहीं एस्केप कर सकेगा, राइट? सो डिफरेंट इलेक्ट्रॉन्स, सम ऑफ दीज इलेक्ट्रॉन्स गेटिंग 9 इलेक्ट्रॉन वोल्ट एनर्जी विल एस्केप विथ काइनेटिक एनर्जी। अच्छा, कोई एक और इलेक्ट्रॉन है जिसने 4 इलेक्ट्रॉन यहां पे खत्म, जिसने सोचो 3.5 इलेक्ट्रॉन वोल्ट्स खत्म कर दिया कोलिजन्स में, बाकी बचा कितना? 5.5 इलेक्ट्रॉन वोल्ट्स इसके पास बचा। 5.5 इलेक्ट्रॉन वोल्ट्स में 5 इलेक्ट्रॉन वोल्ट टू एस्केप द पोटेंशियल बैरियर, बाकी काइनेटिक एनर्जी इक्वल टू 0.5 इलेक्ट्रॉन वोल्ट बचा। सो डिफरेंट इलेक्ट्रॉन्स ऑन द सरफेस वुड कम आउट, some electrons will come out, some electrons will come out with less kinetic energy, some electrons will come out with more kinetic energy।
Yes sir।
है ना? If you
Yes,
give the
sir।
same amount of energy to every electron, then some electrons will not even come out। सबसे आवारा इलेक्ट्रॉन, some electrons will just about come out with zero kinetic energy. Some electrons will come out with more kinetic energy. Some electrons will come out with less kinetic energy, right? अब जो
Yes.
समझदार इलेक्ट्रॉन है वो क्या करेगा? सबसे समझदार इलेक्ट्रॉन, सबसे समझदार इलेक्ट्रॉन, if you give it 9 electron volt, ये सीधे रास्ते चलने वाला इलेक्ट्रॉन, 5 इलेक्ट्रॉन वोल्ट लेके तो बाहर निकल जाएगा, 5 इलेक्ट्रॉन वोल्ट कंज्यूम करके तो ये बाहर निकला, 9 में से बचा कितना इसके पास? 4 इलेक्ट्रॉन वोल्ट। तो ये 9 इलेक्ट्रॉन वोल्ट है ना, इसका मैक्सिमम काइनेटिक एनर्जी, देयर इज एन इलेक्ट्रॉन दैट जस्ट कम्स आउट ऑफ द सरफेस विदाउट कोलाइडिंग, that electron will have maximum kinetic energy because it is just using enough energy to overcome the potential barrier, cross over the surface. The rest it's retaining as its own kinetic energy, uska savings hai wo.
Yes, sir.
Yes, sir.
You know what is happening? Therefore, if you supply energy to a metallic surface, then what all can happen to the electrons? और कोई एक इलेक्ट्रॉन है जो कि 9 इलेक्ट्रॉन वोल्ट दोगे, उसमें से 8 इलेक्ट्रॉन वोल्ट तो वो कोलिजन्स में खत्म कर देगा, ये एक इलेक्ट्रॉन वोल्ट उसके पास बचा, दैट्स नॉट इनफ फॉर इट टू एस्केप द सरफेस. if the let's say the work function of the surface is metal is 5 electron volts, right?
Yes,
Yes,
sir.
sir.
So you understand what is exactly happening here,
Yes,
Yes,
sir.
sir.
right? Now, this time, so like I said, there are various ways to energize the electrons. There are various ways to energize the electrons. One way to energize the electron is if there is an electromagnetic radiation incident on a metal. Incident radiation. Incident radiation of frequency nu, wavelength lambda, which is c by frequency, right? तो इसमें क्या है? इसमें photons है, photon. इस इंसिडेंट बीम में फोटॉन है, और जितना इंटेंसिटी ज्यादा होगा उतना ज्यादा फोटॉन्स होगा, पर एनर्जी ऑफ द फोटॉन डज नॉट डिपेंड ऑन द इंटेंसिटी. एनर्जी ऑफ फोटॉन डज नॉट डिपेंड ऑन इंटेंसिटी. एनर्जी हर फोटॉन का कितना होता है? E is h nu या h c by lambda, which has nothing to do with intensity. Intensity will be about number of photons, but हर photon का intensity mother wave का frequency या mother wave का wavelength पर ही depend करेगा. Intensity of the wave पर नहीं depend करेगा energy of the photon. So energy of photon does not depend on intensity; it only depends on frequency and therefore wavelength. Right?
Yes, sir.
Yes, sir.
अब ये फोटोन है, इस मेटल का वर्क फंक्शन, इस मेटल का वर्क फंक्शन WS, मतलब W is like the potential barrier of the surface electrons, है ना? देखो ये जो प्रोसेस होगा ना एनर्जाइज करने का, मोस्टली जो सरफेस पे होगा, क्योंकि जो अंदर रहेगा ना इलेक्ट्रॉन्स हैं, वो ऊपर आते आते बहुत कोलिजन्स होगा उसको. इवन इफ यू गिव इट एनर्जी इक्वल टू द वर्क फंक्शन, it will undergo a lot of collisions and it may not escape the surface. So if there is a probability of escape that is predominant the top layer of the metallic surface, वहीं से escape करने का chance रहेगा.
Yes,
Yes.
sir.
Deep within, deep in the meat of the metal, you might give it an energy equal to work function, but in that energy will get completely consumed. इस surface पे पहुंचेगा उसके बाद तो work function apply करेगा ना, पर surface तक पहुंचते पहुंचते उसका इतना collisions होगा कि उसमें energy खत्म हो जाएगा.
हाँ सर.
है ना? अब देखो.
Yes, sir.
अब क्या होता है ये photons जो आ रहे हैं, these are bundles of energy like I said with energy equal to hc by lambda या h nu, and with momentum, each momentum equivalent momentum of each photon is h by lambda. अब क्या होगा कि ये एक इलेक्ट्रॉन है, सोचो ये एक इलेक्ट्रॉन है, इस पर ये बंडल ऑफ एनर्जी फॉल करता है. On this electron, this bundle of energy, the photon falls. The photon is incident. Photon incident on the collides with an electron. Photon collides with the electron. ठीक है बेटा?
हाँ सर.
फिर ये इलेक्ट्रॉन क्या करता है? The electron photon को हजम कर जाता है. Swallows the photon. The electron consumes the photon. When I say consume the photon, मतलब उसका एनर्जी ले लेता है. ठीक है? Photon collides with the electron. Electron consumes the energy of the photon. Electron consumes the energy of the photon. अब जब ये मतलब कितना एनर्जी कंज्यूम कर लेगा ये? hc by lambda या h nu.
Yes sir.
Right? So this consumes an energy h nu या hc by lambda. अब इसके पास एक्स्ट्रा एनर्जी आ गया because it has digested the energy of the photon. Right?
Yes sir.
Yes sir.
Yes, sir.
Now for sure देखो अगर ये एनर्जी वर्क फंक्शन से कम है तब तो कोई पॉसिबिलिटी नहीं है एस्केप करने का. अगर ये वर्क फंक्शन या वर्क फंक्शन से ज्यादा है तब इट मे एस्केप. है ना?
Yes sir.
Right?
Yes, sir.
The electron may escape the surface if h nu, yeah, which is hc by lambda, is greater than or equal to the work function. Work function के बराबर होने से भी it is no guarantee that it will escape. है ना?
Yes sir.
Yes sir.
तो इसका मतलब क्या है? वर्क फंक्शन तो मेटल का प्रॉपर्टी है, ये तो कांस्टेंट है, बट ये जो इलेक्ट्रोमैग्नेटिक वेव इंसिडेंट है उसका लेट्स से यू कैन वेरी द फ्रीक्वेंसी एंड देयरफॉर यू कैन वेरी द वेवलेंथ. राइट? व्हिच मींस गामा, the frequency of the wave, frequency of the photon must be greater than or equal to w by h, work function by h, which is Planck's constant.
Yes sir.
Or from this hc by lambda must be greater than or same thing w. That means lambda must be less than or equal to hc by w. Yes or no? Lambda must be less than or equal to hc by w.
Yes sir.
Yes sir.
That means this w by h is the minimum frequency required to have liberation of electrons from the metal surface. मतलब इंसिडेंट एनर्जी का फ्रीक्वेंसी कम से कम w by h होना चाहिए.
Yes sir.
so that the electron has energy at least equal to work function, so that there is a possibility to escape. इस frequency W by H को threshold frequency बोलते हैं. This W by H is called threshold frequency. Which is what? Which is the minimum frequency. ये gamma naught बोलते हैं इसको. Gamma naught बोलते हैं. Gamma naught. This HC by, I'm sorry, this W by H is that minimum frequency, gamma naught, which is required for a possible liberation of the electrons, ejaculation of the electron from the metal surface. This is called the threshold frequency for this metal. This is called the threshold frequency for this metal, and work function of the metal. So what we have to know is the work. Agar if you know gamma naught, then you know that H times mu naught, where mu naught is the threshold frequency, would be the work function of the metal. If mu naught is the minimum frequency required, for liberation of electron from the metal surface, then the work function would be H times mu naught.
Yes,
Right?
sir.
मतलब
Yes, sir.
कम से कम जो इंसिडेंट रे का फ्रीक्वेंसी होगा ना, वो गामा नॉट से तो ज्यादा होना, गामा नॉट और है.
Yes, sir.
सिमिलर वेवलेंथ क्या होना चाहिए? इससे कम होना चाहिए. अगर फ्रीक्वेंसी इससे ज्यादा होगा, गामा नॉट से ज्यादा होगा, तो वेवलेंथ hc by w से कम होना चाहिए. This is the maximum permissible wavelength. This is the maximum permissible wavelength. Lambda naught. This lambda naught corresponds to this gamma naught. Threshold frequency and threshold wavelength are corresponding to each other.
Yes, sir.
ठीक है, wavelength इससे ज्यादा नहीं होना चाहिए, तो maximum possible wavelength is hc by w, which is lambda naught, which is the maximum permissible. दिख रहा है क्या नीचे का?
Yes, sir.
Sure.
So lambda naught, which is hc by w, is the maximum possible wavelength of incident energy, so that there can be a possible liberation of electrons.
Yes, sir.
ठीक है?
Awesome.
Yes, sir.
So lambda को lambda naught से कम होना होगा, और frequency gamma को gamma naught से ज्यादा होगा. There is a higher limit on frequency, there is a lower limit on frequency, that means frequency has to be more than gamma naught, and there is a upper limit on wavelength. Wavelength has to be less than lambda naught, which is hc by work function. So the work function can also be computed from threshold wavelength. This is a threshold wavelength. Threshold wavelength बोलते हैं इसको. Threshold wavelength. This is the threshold wavelength lambda. तो अगर threshold wavelength पता है, तो work function threshold wavelength से निकाल सकते हैं hc by lambda naught, where c by lambda naught is f naught, gamma naught. Lambda has to be less than or equal to lambda naught for the incident energy, and frequency gamma has to be greater than or equal to gamma, where gamma naught is work function by h. Right?
Yes, sir.
Yes, sir.
But if the frequency is greater than gamma naught, a wavelength is less than lambda naught, it doesn't necessarily guarantee liberation of electrons. Electrons may or may not get liberated. That's a probabilistic event. Liberation of electrons is a probabilistic event. Right?
Yes, sir.
Yes, sir.
In fact, एक समझदार इलेक्ट्रॉन भी है, वो निकलने का कोशिश कर रहा है, पर चारों तरफ उसके ना हमारा इलेक्ट्रॉन्स उसके साथ कोलाइड कर करके ना उसको निकलने नहीं दे. तो बोल नहीं सकते कौन सा इलेक्ट्रॉन निकलेगा, कौन सा नहीं निकलेगा. इज अ चांस इवेंट, irrespective of the energy of the photons that are incident. Every electron that is emitted, अब ये इलेक्ट्रॉन क्यों एमिट हुआ? Not because of thermal energy. It's
Yes.
because of energy of the incident beam. Some mostly light energy, let's say. पर कोई जरूरी नहीं है कि light ही हो. पर अगर if the wavelength of this is between 350 to 700 nanometer, then it's visible light. पता है ना? 350 to around 700 nanometer is visible light. So if it is because of visible light, some electrons may, or it can just get emitted because of any kind of radiation. ऐसा कोई जरूरी नहीं है. But generally we use visible light.
Yes, sir.
Yes, sir.
But these liberated electron, if an electron gets liberated, this electron is called a photoelectron. ये जो इलेक्ट्रॉन है इसको कहते हैं photoelectron. And electrons that are liberated are called photoelectrons. And the phenomena is called photoelectric effect. And the phenomena is called photoelectric effect. समझ के?
हाँ सर।
Okay.
अब जो है, can I wipe this off?
Yes, sir.
Yes
अब
sir.
क्या, मेरे को एक बात बताओ, ऐसा क्या पॉसिबल है कि एक फोटोन अपना एनर्जी 2 इलेक्ट्रॉन्स को देगा? नहीं दे सकता.
No, sir.
One photon will get absorbed by 1 electron only. One photon cannot get absorbed by more than 1 electron. So, which means maximum number of, मतलब एक फोटोन के कारण एक ही इलेक्ट्रॉन इजेक्ट हो सकता है, लिबरेट हो सकता है. मैक्स one photon can at best have 1 photoelectron liberated. उससे ज्यादा नहीं हो सकता, बल्कि बहुत सारा यहां जो फोटॉन्स आ रहे हैं वो कंज्यूम हो जा रहा है एनर्जी इलेक्ट्रॉन में, पर इलेक्ट्रॉन फिर भी नहीं निकल पाएगा क्योंकि इसे आवारा इलेक्ट्रॉन.
Yes, sir.
राइट?
Yes, sir.
सो एक फोटोन से एक से ज्यादा इलेक्ट्रॉन नहीं एमिट हो सकता है. मैक्सिमम मतलब इनफैक्ट 1 तो होगा ही नहीं. जनरली क्या होता है, जनरली only 1% of photons result in liberation of photoelectrons generally. Only 1%. 100 photons अगर गिरा है उसमें only 1 photon generally has actually been instrumental in liberation of an electron. तो बाकी 99% का एनर्जी क्या है? थर्मल एनर्जी में वेस्ट हो जाता है. इट रिजल्ट्स इन हीटिंग. 1% का एनर्जी यूज हो रहा है इन लिबरेटिंग द इलेक्ट्रॉन्स, बाकी 99% का एनर्जी गेट्स वेस्टेड और डिसिपेटेड इन हीटिंग द मेटल. मेटल हीटिंग तो होगा, इलेक्ट्रॉन के पास एनर्जी आया और विगरसली मूव कर रहा है, कोलाइड कर रहा है, तो उसका टेम्परेचर बढ़ जाएगा ना.
Yes, sir.
हाँ सर.
है ना?
Yes.
So efficiency is much less than 1%. Efficiency is 1% or less.
Yes, sir.
बल्कि अगर ये गामा is less than gamma नॉट, तब तो efficiency is 0. तब तो कोई चांस ही नहीं है, वर्क फंक्शन ही तुम नहीं ओवरकम कर पा रहे.
Oh, sir.
गामा ग्रेटर देन और इक्वल टू गामा नॉट, फ्रीक्वेंसी ग्रेटर देन और इक्वल टू थ्रेशोल्ड फ्रीक्वेंसी के बाद भी around 1% is or less is the total efficiency of photoelectrons being emitted. With every 100 photons meeting the requirement gamma greater than gamma naught, only maybe 1 photon has resulted in liberation of an electron. Other photons एनर्जी तो इलेक्ट्रॉन ले लेगा पर वो डिसिपेट हो जाएगा एज थर्मल एनर्जी. इट विल नॉट रिजल्ट इन ओवरकमिंग द सरफेस बैरियर और पोटेंशियल बैरियर. ठीक है बेटा?
हाँ सर.
Yes, sir.
Thank you.
Now, see, so one thing for sure, if gamma naught is the threshold frequency, matlab frequency should be higher than gamma naught, then the work function would be h times nu naught. Nu naught is the threshold frequency. Yeah, this is h c by lambda naught. Lambda naught is the threshold wavelength. Frequency should be greater than gamma naught, and wavelength, actual wavelength should be less than lambda naught, so that there is perceivable photoelectric effect, so that there is perceivable liberation of electrons. There is a possibility of liberation, फिर भी guaranteed नहीं liberation of electrons. हाँ? अब सोचो एक photon आया. This is a wave, thermal ray. This is a electromagnetic radiation of wavelength nu. Right? This is a photon. अब ये मत सोचो फोटोन ऐसा दिखता है, ये सिर्फ सिंबॉलिक है. ठीक है?
Yes, sir.
ये इलेक्ट्रॉन अब्सॉर्ब कर लिया, ये एनर्जी इलेक्ट्रॉन अब्सॉर्ब कर लिया. Now, after absorbing this, it has absorbed कितना amount of energy? H nu. H nu is energy absorbed by the electron. This is the energy absorbed by the electron. Right? Out of this, ये सारा इलेक्ट्रॉन वोल्ट्स में कैलकुलेट करेंगे. Out of this, W is used to overcome the surface or potential barrier. ठीक है? तो अब रिमेनिंग कितना हुआ? H न्यू था, इसको एनर्जी मिला, उसमें W यूज किया ये सरफेस तक पहुंचने में, बचा इसका H न्यू माइनस W, सरफेस के जस्ट बाहर पहुंचा, तो ये बाकी एनर्जी इसके पास क्या रहेगा? दो चीजें. इफ दिस एनर्जी, सो इफ दिस एनर्जी इज, no part of this energy is used in collision, then there is maximum kinetic energy remaining with the electron when it comes out.
Yes, sir.
That means if no part of this energy is dissipated by the electron, wasted by the electron in collisions, then this entire energy is available to the electron as kinetic energy. But this can be the maximum possible value of kinetic energy that an electron can have when it comes out. क्योंकि
Yes,
बाकी
sir.
इलेक्ट्रॉन्स में क्या है? ये सारा एनर्जी काइनेटिक एनर्जी में नहीं अवेलेबल होता है when it escapes the surface. Some part of this energy for some electrons will get consumed in collisions. पर जो सबसे समझदार और सबसे एफिशिएंट इलेक्ट्रॉन है वो सारा एनर्जी को काइनेटिक एनर्जी में when it comes out it makes it available. So this is the max. So electrons are coming out of this surface with different kinetic energies, है ना. कोई इलेक्ट्रॉन जो ज्यादा वेस्ट किया अंदर एनर्जी वो कम काइनेटिक एनर्जी से बाहर आया, जो इलेक्ट्रॉन कम वेस्ट किया वो ज्यादा काइनेटिक एनर्जी से आया है बाहर. And an electron that has not wasted any energy in collisions comes out with this amount of kinetic energy, which is maximum possible kinetic energy, right? So maximum possible kinetic energy of electrons या photoelectrons. Photoelectrons बोलते हैं, this is the electrons that are liberated. So if I say photoelectrons, these are electrons that have been liberated. Is Ke max is H nu minus W. So H nu, the energy imparted, is W plus W plus Ke max. This is energy compliance. This is energy compliance. W is the work function. So H nu, which like I said is W plus kinetic energy maximum, where work function is H mu naught. Mu naught is the threshold frequency. Of the incident radiation. So यहाँ से जो बहुत सारा फोटो इलेक्ट्रॉन्स निकलते दिखता है ना, they will come out with different kinetic energies. पर जो सबसे मैक्सिमम काइनेटिक एनर्जी जिस इलेक्ट्रॉन का है ना, वो इस इक्वेशन से निकल सकता है. Kinetic energy of electrons, photoelectrons coming out liberated will vary in general. Kinetic energy of photoelectrons will vary from 0 to Ke max. From 0 to Ke max. Ke max is equation. This equation is called Einstein. This is the work for which Einstein earned his Nobel Prize. Einstein's photoelectric equation. Einstein's photoelectric equation. This is called Einstein's photoelectric equation. Very clearly, देखो kinetic, इससे तो दिख ही रहा है kinetic energy maximum is H into nu minus nu naught. Kinetic energy तो कभी negative नहीं होता, तो ये भी positive ही रहेगा, not greater than or equal to none. Yes or no?
Yes, sir.
Yes, sir.
और एक चीज है कि this entire process of the photon striking the electron and emitting a photoelectron is an instant process. Emission of photoelectron is an instant process instantaneous process, instant process means इसमें जो साथ के साथ होगा, अगर होगा तो साथ के साथ होगा. Time involved is of the order of 10 to power minus 9 seconds. ये सारा process 10 to power minus 9 seconds, which is almost as good as 0 seconds.
Yes, sir.
दो मिनट स्टैंड बाय दे दो बेटा, फिर शुरू करते हैं. Now there is a important experiment related to photoelectric effect and continuous stream of electrons being liberated, referred to as photocurrent. I'll now give you some idea of that experiment. So there is a transparent glass tube. And it has two metallic plates. One is the cathode emitter. The other plate is the anode collector. And this is, there is an ammeter here. Voltmeter here. And the whole thing is connected to this is a battery. This is a sliding contact. But we'll keep this C fixed. But we'll keep C fixed. This is a battery, and this end, this plate, is connected to another sliding contact L. Sliding contact. And we will keep adjusting the position of L. I will not move this for convenience. I will keep this sliding contact fixed at C. It could be the midpoint here, and L I can keep it sliding. अब ये देखो ना बेटा, if L is to the right of C, see C is connected to the negative terminal, L is connected to the positive terminal, right?
Yes, sir.
If L is to the right of C, then the collector has a greater potential compared to the emitter, है ना?
Yes.
देखो collector का potential यहाँ से determine होता है, ठीक है? Because all points to the right of C will be at potentials higher than C, है ना?
हाँ sure.
पर अगर L को यहाँ ले आओ, C को यहाँ ले आओ उल्टा, then L will be at a lower potential compared to C.
Sir.
So if L is to the right of C, see, L to the right of C, collector potential higher than emitter potential. ठीक है क्या? If L coincides with C, both collector and emitter would be at the same potential.
Yes, sir.
और अगर
Yes,
C
sir.
यहाँ आ जाए, L यहाँ आ जाए, तो obviously L will be at a lower potential. This anode will be at a lower potential compared to the cathode, right?
Yes, sir.
Yes, sir.
So I'll slide this. If I want to keep the collector at a higher potential compared to the emitter, then I'll keep L to the right of C. But if I want to reduce the potential of the collector compared to the emitter, then I'll move L to the left of C. Right?
Yes, sir.
Yes, sir.
Now, there is an incident beam. This is through, this is a quartz opening, incident beam. Which is incident on the collector. And I is the intensity of this beam.
Yes, sir.
More the intensity, more number of photons will fall. पर energy of the photon किस पर depend करेगा?
Wavelength.
Wavelength या frequency, right? So there is frequency gamma, nu, and wavelength lambda. So it has packets of energy, photons. The energy of each photon will depend on the frequency or wavelength of the wave. But the number of photons falling and therefore the total amount of energy falling will depend on the intensity. If I is more, then the number of photons falling on this surface, on this metal surface would be higher. I बढ़ा देने से क्या होगा? Total energy falling on the surface would be more, but the energy of each photon is the same. That means there must be more number of photons falling on the surface.
Yes, sir.
You know,
Yes, sir.
per second. Now, I can vary I and gamma both. Nu, let me call it nu. This looks like gamma. Actually, you know, it takes a little bit of an effort to draw nu. Nu should really be like this, and my nu looks like gamma, but you know, इसमें effort लगता है बनाने में. Like this. So I end up drawing gamma in a rush, but this I mean nu. This is what I mean, even though I might write this. Now, what happens? This metal has a certain amount of work function. This has a certain amount of work function. There are incident photons. When would you expect photoelectrons to be emitted? If nu is more than nu naught. And how's nu naught obtained? Work function by h will give me the threshold frequency of the incident, right? So I'm assuming that this nu is more than nu naught. This nu is more than nu naught. Right?
Yes, sir.
Now what happens is, if nu is more than nu naught, you would expect photoelectrons to be emitted. with varying kinetic energies. You would expect photoelectrons to be emitted with varying kinetic energies, right?
Yes.
Yes, sir.
Yes, sir.
अब these photoelectrons, some of these photoelectrons will, अच्छा अब ये देखो, anode is at a higher potential compared to the cathode, that is the collector is at a higher potential compared to this, है ना?
Yes.
तो उसके कारण जो इलेक्ट्रिक फील्ड है वो इस तरीके से है. If this is at a higher potential compared to this, then there is an electric field like this.
Yes,
Yes,
sir.
But
sir.
an electron will accelerate opposite to the direction of the electric field.
Yes, sir.
It's as if this is positive terminal, this is negative terminal. Electrons will get attracted to the positive terminal.
Yes, sir.
So, if L is to the right of C, collector is higher in potential. Electrons क्या होता है? Electrons move from lower to higher potential, whereas positive charges move from higher to lower potential. So electron का tendency है to move from lower to higher potential. So the electron will get accelerated. Electron gets accelerated. Electrons will get accelerated, and some electrons will reach the collector. This is emitter because it's emitting electrons. There is an accelerating potential. Some electrons will reach the surface. Some high energy electrons will reach the collector, right?
Yes, sir.
Yes, sir.
And when they reach the collector, there is a stream of electrons from the emitter to the collector. There is a stream of electrons from the emitter to the collector, right?
Yes, sir.
Or these electrons flow like this through the circuit. These electrons will
Yes,
flow
sir.
like this through the circuit. So there is a current established in the circuit,
Yes, sir.
right?
Yes, sir.
Stream of electrons. Get accelerated from emitter to collector, emitter to collector, stream of electrons will get accelerated.
Yes, sir.
So the emitter will show a deflection, emitter will show a current.
Yes, sir.
Emitter shows current. And this current flowing in the circuit is called a photocurrent. This is called photocurrent. Yeah, sometimes they call it photoelectric current. PEC भी बोलते हैं, photoelectric current या photocurrent. I. Right?
Yes,
Yes,
sir.
sir.
Now, can I wipe this off if you finish copying this?
Yes, sir.
Yes, sir.
अब देखो, if I increase the intensity, keeping the wavelength and frequency constant, intensity, maintaining the same nu and लैम्डा, तब क्या होता है? More photons will be incident, right? More photons incident. ज्यादा photons incident होगा तो what will result? More photoelectrons produced.
Yes, sir.
Yes, sir.
If there are more photoelectrons produced, then there are more photoelectrons reaching this in a given time.
Yes, sir.
Yes, sir.
Yes, sir.
More photoelectrons means more photocurrent. More photocurrent.
Yes, sir.
Right?
Yes, sir.
Yes,
Yes,
sir.
sir.
In fact, photocurrent intensity will be proportional to number of photons, which will be in then turn proportional to number of photoelectrons, and number of photoelectrons will be proportional to the total current. That means intensity and photocurrent will be linearly related.
Yes, sir.
Yes,
Yes,
sir.
sir.
Copy?
Yes, sir.
Yes, sir.
So अगर frequency और wavelength same रखा तो photocurrent I, photocurrent with intensity I, when intensity is 0, there will be no photocurrent. And then it increases linearly. Photocurrent with keeping new constant. New constant है तो wavelength भी constant है obviously. This is intensity. This is photocurrent varying with intensity in this setup. Right?
Yes, sir.
If I finish copying this, I need some room to write. Unfortunately, I can't remove the diagram.
Yes, sir.
Yes, sir.
अब ये देखो, इसको अगर 0 volts बोलेंगे, 0 volts, so this will be say V volts. अगर V potential difference है ना इन दोनों के बीच में, if I call this 0 volts, this will be V volts, where V is the potential difference. किसी को भी तो 0 बोल सकते हैं. I can call this 0 volts, so this will be V volts.
Yes, sir.
Is
Yes,
the
sir.
collector voltage. Collector voltage. With respect to the emitter voltage. This is the collector voltage with respect to the emitter voltage. This V volts will be the reading of the voltmeter. V volts will be the reading of the voltmeter. Right? Collector voltage.
Okay.
Collector voltage. Now, next what I do is keep intensity constant. I constant. ठीक है? And increase collector voltage. And increase collector voltage. कलेक्टर वोल्टेज को बढ़ाएंगे. ठीक है?
Yes, sir.
हाँ, sir.
Obviously electrons are getting accelerated. अब कलेक्टर वोल्टेज बढ़ा दिया तो would you realize that surely यहां से ना the number of photoelectrons emitted will be the same.
Yes, sir.
क्योंकि intensity same है, तो incident photons is the same. So the number of electrons emitted will be the same. Photoelectrons उतना ही emit हो रहा है, right?
Sir.
Since I is the same, number of photons incident is the same. And therefore, number of photoelectrons is also the same, right? Number of photoelectrons will also be the same. Yes or no?
Yes, sir.
But अब ये जो फोटो इलेक्ट्रॉन्स एमिट हो रहा है ना, क्या हो रहा था? Some of them were able to reach the collector. जिसका ज्यादा काइनेटिक एनर्जी था, जिसका कम था, they were not able to reach the collector. Right? But अगर ये पोटेंशियल डिफरेंस बढ़ा देंगे, then even the lower energy photoelectrons will be able to reach the collector.
Yes, sir.
जिसका काइनेटिक एनर्जी कम था यहाँ पर कुछ फोटो इलेक्ट्रॉन्स का, वो भी अब पहुंच सकेगा यहाँ पर.
हाँ सर.
On increasing V, more photoelectrons reach the collector. जो पहले लो काइनेटिक एनर्जी वाला भी था ना, वो एक्सेलरेट करके दे गेट सक्ड इनटू द कलेक्टर. राइट? तो फोटो करंट बढ़ेगा, राइट?
हाँ सर.
That means photo PEC, photo current will increase. पर इस टाइम ना लीनियर इंक्रीज नहीं होता है. क्या होता है? सबसे पहले देखो, मिटा दे क्या ये वाला पार्ट?
Yes, sir.
हाँ सर.
अगर कॉपी कर लिया हो तो बोलो.
Yes, sir.
ऐसा हो रहा है, फोटो करंट वर्सेस कलेक्टर पोटेंशियल. अभी कलेक्टर पोटेंशियल बढ़ा रहे हो तो फोटो करंट बढ़ेगा. क्यों? बिकॉज मोर नंबर ऑफ फोटो इलेक्ट्रॉन्स कैन नाउ गेट एक्सेलरेटेड थ्रू दिस हायर पोटेंशियल डिफरेंस, है ना?
Yes,
हाँ
sir.
सर.
But जब collector potential, सोचो जब when L coincides with C, the collector potential with respect to the emitter is zero. Collector potential can be zero. ये zero था, ये भी zero हो सकता. They could have been at the same potential. तब क्या होगा? Then also, some very high kinetic energy photoelectrons can still reach this because of their own kinetic energy. They can reach this.
Yes, sir.
तो थोड़ा सा फोटो करंट तो तब भी दिखाएगा.
हाँ सर.
Yes, sir.
Right? So थोड़ा सा फोटो करंट तब भी दिखा रहा है. I know. Even when the collector potential and the emitter potentials are same, some electrons, by dint of their own kinetic energy, some very high energy electrons can still make it. तो emitter एक छोटा amount of current I naught show करेगा.
Yes, sir.
अब तो इसका वोल्टेज बढ़ाते जाओ तो करंट बढ़ता जाएगा. राइट? करंट बढ़ता जाएगा. राइट? करंट विल गो ऑन इंक्रीजिंग. बट एक पॉइंट के बाद जितना सारा फोटो इलेक्ट्रॉन्स निकल रहा है ना, फोटो इलेक्ट्रॉन्स तो एक्स्ट्रा नहीं आ रहा है, उतना ही आ रहा है जितना पहले था. अब ये ज्यादा फोटो इलेक्ट्रॉन्स, मोर फोटो इलेक्ट्रॉन्स आर एबल टू रीच द कलेक्टर. बट ऑन इंक्रीजिंग V, at some point of time, all the photoelectrons that are emitted will reach the collector. उसके बाद तो बढ़ने का रहेगा नहीं.
Constant हो
No,
जाएगा.
sir.
है ना? उसके बाद क्या हो जाएगा? सैचुरेट कर जाएगा करंट. क्योंकि जितना फोटो इलेक्ट्रॉन निकल रहा है ना, एक सर्टेन पोटेंशियल पर ना सारा रीच कर जाएगा. उसके बाद तुम कितना भी बढ़ा लोगे, करंट और नहीं बढ़ेगा, तो इस करंट को कहते हैं आई सैट, सैचुरेशन करंट, सैचुरेशन करंट। इसको कहते हैं सैचुरेशन करंट। समझ रहे हो?
हाँ
हाँ
Yes, sir.
सर।
अब देखो, अब व्हाट आई डू इज, इसको ना कॉन्टैक्ट को सी के टू द लेफ्ट ले आएंगे, इस एल, इफ एल is brought to the left of C, then collector potential will be lower. Emitter potential, isn't it? Collector potential will be then lower than emitter potential. Yes or no?
yes sir,
यस सर।
तो मतलब ये अगर 0 वोल्ट है तो ये नेगेटिव वोल्ट होगा,
हाँ सर,
ये
Yes,
नेगेटिव
sir.
हो जाएगा। समझ रहे हो? So if this is 0 volts, this will then become say minus V naught volts, minus V volts, right?
yes sir,
Yes, sir.
अब क्या होगा? अब जैसे जैसे ये this is becoming more and more negative, अब इलेक्ट्रिक फील्ड किस डायरेक्शन में होगा? ये 0 वोल्ट से ये माइनस वोल्ट, तो एज इफ दिस इज पॉजिटिव एंड दिस इज नेगेटिव, अब इलेक्ट्रिक फील्ड इस तरफ होगा।
हाँ सर,
Electrons don't want to move in the direction of the electric field.
yes sir,
Now the electrons will get retarded.
yes sir,
Now the electrons will retard. Will retard. ठीक है? As you go on making it more and more negative, -1 volts, -2 volts, -3 volts, है ना? तो क्या होगा? इलेक्ट्रॉन का रिटार्डेशन बढ़ता जाएगा, and fewer electrons will reach here.
yes sir,
Yes, sir.
So if the collector voltage is made more and more negative compared to the emitter voltage, then current will decrease because fewer and fewer electrons will reach.
yes sir,
अब रिटार्ड हो रहा है इलेक्ट्रॉन्स, तो जो हाई एनर्जी इलेक्ट्रॉन भी था ना यहाँ पे ओरिजिनली, वो रिटार्ड होके बेचारा यहाँ तक पहुंच ही नहीं पा रहा है।
हाँ
Yes,
सर,
sir.
So now if the collector voltage is made more and more negative, then the photocurrent will go on decreasing. Photocurrent will go on decreasing. Eventually at some V equal to minus V naught, at some V equal to minus V naught, photocurrent will become 0.
yes sir,
For some V equal to minus V naught, photocurrent becomes 0. अब तुम इंटेंसिटी बढ़ा भी दोगे ना तो कुछ फर्क नहीं पड़ेगा अगर माइनस वी नॉट, क्योंकि इंटेंसिटी तुम ज्यादा इलेक्ट्रॉन्स प्रोड्यूस कर रहे हो, पर ये इलेक्ट्रिक फील्ड इस डायरेक्शन में इतना ज्यादा है कि इतना रिटार्ड कर देता है, नो इलेक्ट्रॉन इज एबल टू रीच। खाली ज्यादा इलेक्ट्रॉन होने से क्या फर्क पड़ेगा, राइट?
Yes, sir.
यस सर।
So then this minus V naught, the potential of this with respect to this negative, मतलब अगर ये 0 वोल्ट है, ये minus V naught volts, this is V naught less than this, the collector voltage is V naught less than the emitter voltage, है ना? This potential at which the photocurrent becomes 0, this V naught is called stopping potential. This V naught is called stopping potential. मतलब अगर कोई बोले स्टॉपिंग पोटेंशियल इज 10 वोल्ट्स, मतलब क्या है? कि अगर ये 0 volts होगा और ये -10 volts हो जाएगा, then there'll be no photo current. There'll be no photo current.
Yes, sir.
Yes.
This is stopping potential when the current becomes 0. This is stopping potential. मतलब जो मैक्सिमम काइनेटिक एनर्जी वाला फोटो इलेक्ट्रॉन था ना, वो भी नहीं पहुंच पाएगा
हाँ सर.
उस मतलब if this is V naught less than this, then the highest kinetic energy photoelectron will also not reach this. So अगर V naught is the stopping potential, अगर ये कॉपी कर लिया है तो बोलो.
हाँ
Yes,
सर.
sir.
मतलब this has to be V naught less than this for an electron to not reach this. तो maximum kinetic energy वाला photo electron है ना, so यहाँ से यहाँ this is 0 volts, this is minus V naught volts, और there is a maximum kinetic energy वाला photo electron जो निकल रहा है KE max वाला, which is half m mass of the photo electron V max squared. ये मास ऑफ इलेक्ट्रॉन ही होगा. वो भी क्या हो रहा है ना, क्योंकि इलेक्ट्रिक फील्ड इज लाइक दिस, इट विल गेट रिटार्डेड लाइक दिस, तो वो जस्ट अबाउट यहां पहुंच रहा है स्टॉपिंग पोटेंशियल पर. दैट मींस इट नाउ वर्क एनर्जी थ्योरम से व्हाट इज, सो यहां इसका काइनेटिक एनर्जी मैक्सिमम था, यहां इसका काइनेटिक एनर्जी 0 हो गया. जो मैक्सिमम काइनेटिक एनर्जी वाला फोटो इलेक्ट्रॉन था, इट हैज मैक्सिमम काइनेटिक एनर्जी और जस्ट 0 हो गया. तो बाकी तो इसके पहले 0 हो जाएगा. जो लोअर काइनेटिक एनर्जी वाला है वो तो उसके पहले, यहां तक कलेक्टर्स के पहुंचने के पहले ही 0 हो जाएगा उसका काइनेटिक एनर्जी, राइट?
Yes, sir.
हाँ सर.
Yes, sir.
है ना? तो अब क्या है, व्हाट इज द वर्क डन? व्हाट इज द वर्क डन? Work done on the electron would be E into change in potential minus V naught minus 0, minus V naught minus 0. That's the work done by the electric field.
Yes, sir.
Yes sir.
And that must be change in kinetic energy from work energy theorem.
Yes sir.
Kinetic energy, this is the work done by the electric field. Work done by the field. Q into change in potential. Q is the charge of the electron. Change. And that must be change in kinetic energy 0 minus half m V max squared. That means half m V max squared is EV naught. इससे stopping potential निकाल सकते हैं. So maximum kinetic energy, K max, kinetic energy maximum would be E times V naught. अब क्या करेंगे? Realistically क्या करेंगे ना? ये एक for a certain V equal to V naught, that means this becomes minus V naught. This is 0 volts. The emitter shows no current. The ammeter shows no current. तो एक्चुअली V naught तो एक्सपेरिमेंटली निकाल सकते हैं, उससे Ke max कैलकुलेट कर सकते हैं.
हाँ सर.
I can find the stopping potential. I can keep adjusting this slider. इसको C के लेफ्ट में ले गए और लेफ्ट में ले गए तो V naught का वैल्यू बढ़ता गया. At a certain V naught, ammeter will show 0 reading. That V naught is the stopping potential.
Yes sir.
And that V naught is reflected here. यहाँ पे दिखाएगा वो V naught इस वोल्टमीटर में.
हाँ सर.
There is a certain V equal to V naught where this shows no deflection. That's my stopping potential.
Yes sir.
Equal to minus V. अब वो उससे क्या हो जाएगा? ये माइनस हो जाएगा, ये माइनस, ये प्लस हो जाएगा. तो ये नेगेटिव V naught है, ये 0. Right?
Yes,
Yes,
sir.
sir.
So maximum, if you have carried out this experiment and obtained the stopping potential का magnitude V naught. Stopping potential में क्या है? The potential of this is V naught less than this. मतलब अगर ये 0 है, this is minus V naught. Then V naught is called the stopping potential, where the collector is V naught volts less than the emitter. Right? उससे you can find the maximum kinetic energy of the photoelectrons that are emitted. You can calculate the maximum kinetic energy of the photoelectrons emitted. You know what I'm saying?
Yes, sir.
Yes, sir.
So in my photoelectric equation, H nu is work function H nu naught, work function W, which is H nu naught, plus Ke max, this was my photoelectric equation, and this is W plus EV naught. Kinetic energy maximum would be EV naught. Yes or no?
Yes, sir.
Yes, sir.
Right? Now, अब देखो बेटा, ये इंटेंसिटी I पर, and do you also realize this maximum kinetic energy of a photoelectron will not depend on intensity, it will depend only on frequency of the incident radiation, right?
Yes, sir.
So very important. Can I write this portion now?
Yes, sir.
Yes, sir.
K max depends only on the frequency nu of the incident radiation the frequency nu of the incident radiation, yes or no?
Yes, sir.
Not on intensity. Intensity will tell you the number of photoelectrons produced, but the maximum kinetic energy of photoelectrons will depend only on the frequency of the incident radiation, nu.
Yes, sir.
अब अगर तुम इंटेंसिटी बढ़ा दोगे बेटा, तो अच्छा, stopping potential depends on Ke max, which in turn depends on nu. So, which means stopping potential V naught also depends only on nu. Because Ke max depends only on nu, so stopping potential will only depend on nu. तो अगर nu सेम रखोगे और इंटेंसिटी बढ़ाते जाओगे, तो स्टॉपिंग पोटेंशियल चेंज नहीं होगा. कंफ्यूजन है क्या बेटा?
No, sir.
No, sir.
Sir, একবার repeat করুন।
আমি বলছি that the maximum kinetic energy of photoelectrons, it's only depending on nu, it's not depending on intensity.
Yes, sir.
তার মানে এই যে stopping potential will also depend only on nu.
Yes, sir. Yes, sir.
Usually incident radiation, if you maintain the same nu, even if you increase the intensity, stopping potential will not change, will remain V naught.
Yes, sir.
Come on.
Yes, sir.
So now what happens? What you have to understand now is, suppose this is my saturation current for intensity I1. Intensity I1. This is my stopping potential minus V. Right. Now I maintain the same frequency, but I increase the intensity. So stopping potential change होगा क्या? नहीं होगा ना?
No, sir.
But if I increase the intensity, then what happens? More number of incident photons and more number of photoelectrons.
Yes, sir.
So saturation current भी बढ़ेगा.
Sir.
So if I increase the intensity, saturation current will increase. I2, which is more than I1. So if I increase the intensity, saturation current will increase, but stopping potential will remain the same. Yes or no? If nu is maintained constant, if nu is maintained constant, then and intensity increase, stopping potential will remain same, saturation current will increase. That means ISAT increases. ISAT increases. देखो इसका सैचुरेशन करंट ये वाला है, इसका सैचुरेशन हायर इंटेंसिटी में सैचुरेशन करंट ज्यादा होगा। पर सिंस फ्रीक्वेंसी दोनों का सेम है, सेम फ्रीक्वेंसी, तो स्टॉपिंग पोटेंशियल सेम रहेगा, बिकॉज़ स्टॉपिंग पोटेंशियल विल डिपेंड ऑन मैक्सिमम काइनेटिक एनर्जी ऑफ photoelectrons which only depends on the frequency of the emitted frequency of the wave. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
So this is another characteristic you must know. On increasing intensity, maintaining the same frequency, I have the same stopping potential, but I have higher and higher saturation currents. Higher saturation current because now there is higher intensity, but there is greater availability of photons and greater availability of photoelectrons. So saturation current बढ़ सकता है ना on increasing the. So do you understand this graph?
Yes, sir.
Yes, sir.
Yes, sir.
अब सोचो जितना ज्यादा न्यू रहेगा उतना ज्यादा काइनेटिक एनर्जी रहेगा, मैक्सिमम काइनेटिक एनर्जी. द ग्रेटर द वैल्यू ऑफ न्यू, द ग्रेटर वुड बी द maximum kinetic energy of the photons,
Yes, sir.
Yes, sir.
photoelectrons,
Yes, sir.
and greater would be the stopping potential. मतलब अगर हाई एनर्जी बीम इंसिडेंट है ना, न्यू हाई मतलब हाई एनर्जी बीम, हाई एनर्जी बीम के लिए न्यू ज्यादा है तो काइनेटिक एनर्जी मैक्स ज्यादा रहेगा, तो स्टॉपिंग पोटेंशियल ज्यादा रहेगा.
हाँ सर.
Yes, sir.
Yes or no?
Yes,
Yes,
sir.
sir.
So if you allow me to wipe this.
Yes, sir.
Yes, sir.
If nu is increased, nu increase मतलब higher energy of photons, it's a high energy beam. If nu is increased, then Ke max increases and stopping potential increases. V naught increases in magnitude. But so I'm assuming I is maintained constant. अगर सेम इंटेंसिटी में तो अगर इंटेंसिटी सेम है, मींस द सेम नंबर ऑफ फोटो इलेक्ट्रॉन्स विल बी एमिटेड.
Yes, sir.
Yes, sir.
If the same number of photo electrons are emitted, that means saturation current will remain the same,
Yes, sir.
Yes, sir.
right? तो उसका ग्राफ photo current versus V. ये V नॉट 1 है और ये फ्रीक्वेंसी न्यू 1 है. उसका फोटो करंट वर्सेस V ऐसा है और उसका स्टॉपिंग पोटेंशियल है. अब न्यू बढ़ा दिया, न्यू 2 कर दिया, न्यू 2 मोर देन न्यू 1, तो स्टॉपिंग पोटेंशियल बढ़ जाएगा.
हाँ सर.
Yes, sir.
ये माइनस V नॉट 1 की जगह माइनस V नॉट 2 हो जाएगा. बट सैचुरेशन करंट ना सेम रहेगा. दिस इज फॉर न्यू 2, दिस इज फॉर न्यू 1, न्यू 2 मोर देन न्यू 1. समझ रहे? सो स्टॉपिंग पोटेंशियल यहाँ V नॉट 2 है, यहाँ V नॉट 1. फ्रीक्वेंसी कम होगा तो स्टॉपिंग पोटेंशियल कम होगा, फ्रीक्वेंसी कम होगा तो काइनेटिक मैक्सिमम काइनेटिक एनर्जी कम रहेगा तो स्टॉपिंग पोटेंशियल कम रहेगा. फ्रीक्वेंसी बढ़ा दोगे, गामा 2 कर दोगे, गामा 2 मोर देन न्यू 2 मोर देन न्यू 1, then stopping maximum kinetic energy will increase, stopping potential will increase, but saturation current will remain the same. Saturation current remains the same. ये saturation current ऐसा है. Saturation current क्यों बोलो तो, बोलो क्यों?
Intensity same.
Intensity same होले की होवे?
Number of photoelectrons is same.
Number of photoelectrons is the same. That means maximum saturation current will remain the same.
Yes, sir.
I know. This is how this varies, right?
Yes,
Yes.
sir.
Now, all good.
Yes, sir.
So must remember that maximum kinetic energy would be E times stopping potential obtained from this experiment, right?
Yes, sir.
In a photoelectric phenomena. Now, realize, can I wipe this off?
Yes,
Yes,
sir.
sir.
See, h nu is the frequency, is work function plus kinetic energy maximum. Right? That's a photoelectric phenomenon where Ke max is E times V naught, where V naught is the stopping potential. I know.
Yes, sir.
अब अगर तुम Ke max therefore would be h nu minus work function. So if you have to draw the graph of Ke max versus nu, maximum kinetic energy of emitted photoelectrons versus nu. देखो nu equal to nu naught तक तो कोई photoelectron, this is threshold frequency. Threshold frequency. यहां तक तो कोई photoelectric phenomena होगा ही नहीं. So no photoelectrons will be emitted. Kinetic energy 0, right?
Yes, sir.
फिर उसके बाद do you realize this is like y equal to mx plus c? Straight line है. K versus nu is a straight line.
Yes, sir.
उसका y intercept क्या है? Y intercept minus w है. Minus w है y intercept.
हाँ, sir.
और इसका slope क्या है? Tan theta. Slope of this is h. है ना? Ke max versus nu का ये ग्राफ होगा. Up to nu naught तो कोई photoelectric phenomena होगा ही नहीं. If nu is more than nu naught, then Ke max will vary linearly with nu. Will go like this.
sir.
Right?
हाँ, sir.
Yes, sir.
That's Ke max with nu. There is no photoelectric phenomena up to nu naught, and then it linearly increases with nu. Right?
Yes, sir.
Yes, sir.
Yes, sir.
Stopping potential versus frequency. K max, maximum kinetic energy is E times V naught, which is h nu minus w, right? So stopping potential h by E, nu minus w by E. अब देखो, V naught versus nu is also a straight line. Stopping potential versus nu. अच्छा देखो, mu equal to nu naught तक तो कोई stopping potential का जरूरत ही नहीं है क्योंकि no photoelectric phenomena कोई नहीं रहा है. उसके बाद it's increasing linearly with nu. इसका y intercept हाँ आता नहीं है, just would be minus w by e would be the y intercept, and इसका slope theta tan theta of this stopping potential versus
G max के ग्राफ की तरह ही है.
h by e है ना बेटा.
हाँ, sir.
और इसका y इंटरसेप्ट क्या होगा? माइनस the work function divided by the charge on the electron. E is 1.6 into 10 to the power minus 19 coulombs. Understood this?
Yes, sir.
Yes, sir.
All right. I have to teach you a few more things, but part 1 of photoelectric effect we've been able to cover in the class today.